What if you looked up tonight and saw not one moon but two? Not a tiny dot beside the familiar moon. A second, full-sized lunar world glowing across the sky, pulling on Earth with its own gravity. The oceans would rise higher. The calendar would become confusing. And in the long run, Earth itself could be pushed into a very different future. To make this scenario scientifically useful, let's be precise about the premise. Earth, the Sun, and our current moon stay the same. We add one new moon with the same mass and size as the existing one. We place it at roughly the same distance from Earth, about 384,000 kilometers away, but 60 degrees ahead of the original moon in its orbit. That arrangement matters. Simply dropping two moons into the same orbit would probably end in a collision or a violent gravitational slingshot. But two objects of similar mass can share an orbit in a triangular configuration, with Earth forming the third corner. It is not guaranteed to last forever, but it gives our second moon a plausible starting point. At first, the visual change would be spectacular. Each moon would still take about 27 days to orbit Earth relative to the stars. From the ground, they would slowly move across the sky, separated by about 1/6 of the celestial circle. Sometimes both would be visible together. Sometimes one would be rising while the other was setting. And occasionally, their positions would make them appear close enough to create stunning conjunctions, with two bright disks hanging over the horizon. But the sky would not simply become twice as bright. The full moon is roughly 400,000 times fainter than the sun, but it is still bright enough to cast shadows. Two full moons would provide about twice the moonlight, making the darkest nights noticeably brighter. That could affect animals that use darkness for hunting, hiding, migration, or reproduction. Still, the increase would not resemble daylight. A full moon provides only around 1/millionth of the sunlight reaching Earth. Two moons would turn a moonlit night into a brighter moonlit night, not a second daytime. The bigger immediate effect would be gravity. The moon's pull stretches Earth slightly, creating two tidal bulges in the oceans. Because Earth rotates beneath those bulges, most coastlines experience rising and falling tides. Add a second moon of equal mass, and the strength of the tidal forcing would depend on where the two moons are in relation to each other and to the coastline. When both gravitational pulls reinforce one another, high tides could become substantially higher than today's typical lunar tides. In a simplified case, the lunar part of the tide could approach twice its current forcing. That does not automatically mean every tide doubles, because the sun also contributes. Ocean basins respond differently, and coastlines can amplify or weaken the effect. But during an alignment involving both moons and the sun, some regions could see extreme spring tides. Existing low-lying coastal areas would flood more often. Harbors, deltas, tidal wetlands, and island communities would face a new rhythm of regular inundation. Then, a few days later, the moons could pull in different directions. Their tidal effects might partly cancel, producing unusually weak tides in some locations. The result would not be one permanently giant ocean tide. It would be a more complicated, more powerful tidal calendar, with stronger swings between high and low conditions. Those tides would also reshape Earth's rotation. Our current moon is slowly transferring rotational energy from Earth into its orbit. That is why Earth's day lengthens by roughly a few milliseconds per century, while the moon gradually moves away from us by about 3.8 centimeters per year. With two moons, the total tidal breaking could be approximately doubled, assuming the two bodies remain at similar distances. Earth's day would still change very slowly on human timescales, but over millions and billions of years, the difference would accumulate. Days would lengthen faster, and both moons would drift outward. There is another complication. The moons would tug on each other. In our starting arrangement, each moon would disturb the other's orbit. Their distances from Earth would vary slightly. Their orbital speeds would exchange energy. Over time, this could produce a long-term pattern of resonances, shifts, and instabilities. If the configuration remained stable, the two moons could orbit Earth for billions of years. If small disturbances grew, one might migrate inward, the other outward, or one could eventually be ejected from Earth's orbit. The exact outcome would depend on their starting positions, orbital inclinations, and the influence of the sun. So our thought experiment is not a permanent guarantee. It is a snapshot of a physically possible arrangement, followed by the consequences that would begin immediately. The ocean would not be the only part of Earth responding. The solid planet itself flexes under lunar gravity. Earth's crust rises and falls by as much as several tens of centimeters in response to the moon and sun, even though we do not notice it beneath our feet. A second moon would increase that flexing. In certain regions and alignments, the extra stress could slightly influence volcanic systems, faults, and underground fluids. That does not mean every earthquake would be caused by the moons. Earth's tectonic energy is vastly larger and more complex, but a second moon would add another repeating gravitational signal, potentially nudging systems that were already close to failure. The atmosphere would feel subtler effects. The tides raised in the oceans and solid Earth create friction and heat. Doubling the lunar contribution would not boil the planet, but it would increase tidal energy dissipation. More energy would be converted into heat, especially in shallow seas and coastal regions. The length of the month would also become difficult to define. We could keep using the familiar moon cycle, but the second moon would have its own phases. Depending on its position, the two full moons might arrive days apart or appear together on a regular schedule. Imagine a calendar with two repeating lunar cycles. Religious observances, traditional months, animal breeding patterns, and nighttime human activity would all have to adapt. A full moon would no longer be a single obvious event. It might mean one moon is full, both are full, or the brighter combined phase is being measured. Eclipses would become much more common and much more complicated. Our current moon produces solar eclipses because it appears almost exactly the same size as the sun in the sky. The second moon would have nearly the same apparent size. Each could cross the sun independently, and sometimes both could be involved in the same general event. But two moons do not guarantee constant eclipses. Their orbital planes could be slightly different, just as the current moon's orbit is tilted about 5 degrees relative to Earth's path around the sun. Even so, the number of possible eclipse events would increase. Some years could contain multiple spectacular solar eclipses visible from different parts of Earth, along with more frequent lunar eclipses. And then there is Earth's tilt. The moon helps stabilize Earth's axial orientation by exerting a strong gravitational torque. Without our moon, Earth's tilt could vary much more chaotically over very long periods, creating severe climate changes. Two moons would provide more total angular momentum and more gravitational influence, which sounds automatically stabilizing. But the real answer depends on their orbital arrangement. Two moons could reinforce the stabilizing effect, or their combined gravitational rhythm could introduce new variations. Earth's tilt would not instantly change, but over millions of years, the climate system could experience a different pattern of long-term seasons and ice ages. Life would adapt, but not uniformly. Coastal ecosystems might expand in some places and collapse in others as tidal ranges changed. Intertidal zones would become larger, harsher, and more dynamic. Nocturnal animals would face brighter nights, while species that depend on precise lunar timing might evolve around two separate cycles. Humans would adapt technologically, too. Coastal defenses would need to account for stronger and less predictable tide combinations. Space agencies would track the moons constantly. Satellites and spacecraft would need new trajectories, because lunar gravity assists would become more complicated and orbital calculations less forgiving. The most dramatic possibility comes at the end of the chain. If the two-moon system became unstable, Earth might eventually lose one moon, gain a distant companion, or witness a catastrophic collision. A collision between lunar-sized worlds would release energy far beyond any human weapon. It could create a debris ring, trigger global earthquakes, vaporize enormous amounts of rock, and leave Earth with a temporary second moon made of fragments. But that is not the inevitable result. With a carefully chosen orbit, two moons could remain companions for geological timescales. So Earth with two moons would not be a permanently brighter, more romantic version of our world. It would be a planet with stronger tides, more complicated eclipses, faster rotational evolution, altered ecosystems, and a gravitational system that demanded constant attention. The lesson is that a moon is not just something we see in the sky. It is an engine quietly reshaping oceans, crust, climate, biology, and time itself. Add a second one, and Earth would still be recognizable, but it would no longer be the same planet. Let's